Anyway, it's a pleasure to welcome friend and former math onco faculty member that's now MD Anderson, trailblazing his new enterprise. And we're going to hear a bit about it, or at least I thought we were, but he's going to mix it up a bit. So Heiko's going to make it entertaining, I'm sure.
Okay, challenge is on. Hello, thanks Sandy for having me. Thanks Sandy, Christian for organizing that. It's nice to be back at a beautiful beach at the Gulf. So Galveston is not quite as beautiful as St. Pete, but so it's nice to be back here. So I'm going to talk a bit about radiation biology and math modeling. And just like Russ, I'm going to focus a bit more on the didactic side, and hopefully some of that is useful to some of you. So we're going to talk about radiation. As most of you probably know, radiation is one of the 5 mainstays of cancer treatment. The second oldest, it's difficult to read on this contrast. So it's surgery, radiation, traditionally chemotherapy, targeted therapy, and immunotherapy. So radiation been around since November 1895 by this gentleman down there on the stamp, Konrad Röntgen. And next to it, you can see the first X-ray image that was ever taken. Hope you can somewhat guess that that's the picture of a hand of his wife. You can see the wedding band on one of the fingers. So this was in November 1895. In February 86, this was published in Science. So it took about 4 months to get this into Science. The article was called On a New Kind of Rays, and X as the mathematical unknown made this into X-rays. And exactly 5 years later, he got the Nobel Prize in Physics for this. So for the grad students in the room, in a span of 5.5 years, you can go from invention to Nobel Prize. So accept that challenge. So on the right-hand side, you can see a couple of pictures of cells. Green is DNA nuclear stain. No, blue is DNA nuclear stain. Green is fibronectin. So everything you can see, green is a fibroblast. Everything that's blue and not green is a cancer cell. Color-coded in red is DNA damage repair proteins. So, that's a great contrast. You may guess that there's like one red dot here. If you come up here, you can see it. So there's some DNA damage repair going on in this cell. But after 5 gray of radiation, you hopefully can appreciate that there's more cells that light up in a bit more red. So what's happening? Radiation causes DNA damage. It's high energy that is shot into the body. As this energy slows down, as these photons slow down, they release energy. They can cause direct damage to the DNA, or they can create reactive oxygen species, and then those harm the DNA. There's 2 kinds of breaks. A single strand break, very easy to repair. Double strand break, potentially more difficult to repair, because if you break the strand apart, you can miss repair, or some DNA base pairs might be missing, and then you begin to encode information that may no longer be viable for the cell to continue to divide. So radiation itself doesn't kill cells, it causes damage, which makes these cells no longer viable. Depending on where the cells are in the cell cycle, the response to radiation might be different. Here you can see a very common plot where it's the surviving fraction as a function of dose. That's usually on a log scale, and you get these very characteristic shoulder-looking curves. And you can see that color-coded different cell cycle phases. So depending on where the cells are, they may be more or less sensitive to radiation. And of course, cells that are not actively dividing, that may be quiescent or hypoxic, are much more resistant to radiation. Because if you're not dividing, if your DNA is bundled up and not exposed, it's much less likely to create DNA damage. And also, if you're hypoxic, there's no oxygen, you cannot generate reactive oxygen species, as shown here on the left. So how do we measure radiation response? It's a clonogenic assay that some of you may have seen before. So what you can see there in the top row is individual cells plated in a petri dish. Let them grow for 4 weeks, and then you count colonies. So every single dot or spot you can see. Can anybody actually see the laser pointer? Oh, great. So every spot you can see in your petri dish, if you zoom in, is actually a colony of cells. So if this colony is large enough, we say, okay, this colony has formed. We count how many colonies have formed after no radiation, and then we count how fewer colonies we get after increasing doses of radiation. We can plot that again as the surviving fraction over dose, and we get these experimental data. We can then use a mathematical equation shown in green here, known as the linear quadratic model, to fit two parameters, alpha and beta, which is a linear component and a quadratic dose dependent. That's why it's called linear quadratic. And we can try to fit these data by calibrating these alpha and beta parameters. And these two parameters are the cell-line specific, patient specific, tumor specific radiosensitivity parameters. So with this, with increasing radiation dose, we get more and more probability of controlling the tumor. Everything on the left-hand side of this curve means treatment is ineffective. And yes. Awesome. Fine with me. How's that? But now I'm sharing this here, so the Zoom shares the wrong screen. Do I have a mouse? Hold on, we can figure that out. Where's my mouse? There. Okay, who knows how to operate Zoom? Stop share. Share. Desktop 2. Share. Presentation. Play. Now we're gonna switch this again. And now we should be golden, no? Can you now see the right thing? Who set that up for me? All right. So where were we? Okay, everything on the left-hand side of the tumor control probability curve is ineffective. So everything to the right, the more dose we give, the more likely it is we kill the tumor. Unfortunately, we cannot give a dose that is too high to be toxic for the patient and for the tissue. For that, we have a tissue complication probability curve shown in orange here. So everything on the right-hand side of this curve is too toxic. So this hopefully gives us a therapeutic window between those two curves where we can find the acceptable dose that induces a large likelihood of tumor control and a low risk of tissue toxicity. So when we are modeling radiation therapy mathematically, we can, of course, start with the tumor growth model. Here, a very simple example of exponential growth. You get a beautiful exponential growth curve. And then radiation is giving at discrete moments, right? At the time we deliver radiation is only a few minutes. So, oops, at this point in time, we usually stop a continuous simulation, apply the survival fraction, and start treatment again. Then we do that as many times as we have to. Now, big shout out to Russell and Kristen, who published this paper in 2010, which I think is probably the best radiation modeling paper that was ever published. It's also in my top 3 of math oncology papers of all time. If you haven't had a chance of reading that, I would highly recommend that. Why is this awesome? Because first of all, here's a continuous form of integrating radiation into... Why is this moving? Did you set up that my slides advance automatically? You know I'm gonna run late and say, oh, let's put 1 minute per slide to make sure he is, but I see how it goes. So here you can see a continuous form of radiation in there. It's like a Kronecker delta function that is this radiation response term is 0 when radiation is not given, or not 0 whenever radiation is given. What's also nice is that there's a beautiful correlation of a mathematical model parameter, in this case the growth rate, against radiation sensitivity. And this makes sense. We know that cells that are more actively proliferating are much more sensitive to radiation. What's also important is what I've highlighted here in orange, is that Kristen and Russ have done a logistic growth and a logistic radiation response. So this is known as the Norton-Simon hypothesis from 1977, which states that the rate at which a tumor shrinks in response to cytotoxic therapy is proportional to its growth rate before treatment. What does this mean? When tumors grow in a logistic or Gompertzian manner, then they slow down. So they have exponential growth early on, and later on you get less and less growth as you approach a carrying capacity. So therapy is most effective whilst the tumor is growing rapidly. Again, you need proliferating cells for cytotoxic therapies to be successful. Therefore, early and aggressive treatment is more effective than later on. So what does it mean mathematically? If we have a logistic growth model and we simulate, unbelievable. Yes. Suddenly the green bar is gone. Am I sharing the wrong screen again? Ah, cool. Just want to make sure people are still paying attention. So what you can see if you have a logistic growth as shown here on the left-hand side, if we are now applying an exponential radiation response, as shown here, if you get like a 70% reduction here and a 70% reduction here, you can see you're massively overestimating the response to radiation. If you're doing the logistic growth and the logistic radiation response, you can see that we take away a much larger proportion of cells here than as the tumor proliferation rate slows down. And this concept we took forward in our lab to develop a model that we called PSI, or the Proliferation Saturation Index, where we took the logistic growth and the logistic radiation response, and we defined PSI as the tumor volume at beginning of treatment over its carrying capacity. Why is this important? If you look at two patients, patient one in a black curve, patient two in a red curve, they can have a different history of their disease and a different future of their disease, but at some point in time, shown here as time point 0, they may present in the clinic with identical disease, with identical tumor burden, identical stage. So for all intents and purposes, these two patients would be treated with similar radiation therapy. But as you can see, patient 2 in red has a much steeper first derivative at this time point, so much more proliferative disease, so a lower proliferation saturation than the black patient, and therefore a much steeper response to radiation. That's the theory, folks, right? Now we went ahead to see, does this make any sense? So Inakshi, when she was an undergrad in the lab, looked at non-small cell lung cancer data. What you can see are these red circles are daily CT scans of the tumor volume over time. And we were able to train the model I just showed you, which has 3 parameters: growth rate, radiation response rate, and PSI. And we were able to show that by only having PSI as a global parameter, as a patient-specific parameter, and both the growth rate and radiation sensitivity as a global parameter, so the same for all patients, we can fit this data very well. So you can see 2 patients. The blue curve is the model fit to data. And down here in this plot, you can see all 27 patients in this cohort, where we plot simulated volume against observed volume. And for a single parameter model, that fit is reasonably well, I would argue. Now then, Tom and Mohammed in the lab took this forward into head and neck cancer. Same thing, the model with just 1 parameter PSI can explain patient-specific and overall cohort data very well. What's important is PSI does not correlate with initial tumor volume. So we cannot say if you have a larger tumor, you have a larger PSI or any combination thereof. But what we can say is that PSI very strongly correlates with how the tumor volume shrinks during course of radiation. So taking this concept forward, we took data of Jimmy Cordell at the Moffitt Cancer Center in Tampa, Florida, and a separate cohort of head and neck cancer patients from Dave Fuller from the MD Anderson in Houston, Texas. And what Mohammed has done here is plotting the relative tumor volume over time for each individual patient. So there's about 39 patients in this cohort. And so this is called a spaghetti plot for apparent reason, I guess. Each patient starts at their own 100%, and you can see how this tumor volume changes for each individual patient. First thing, I hope you can appreciate that there's quite heterogeneity in response. The next thing is color-coded in black, patient with local regional control. Color-coded in purple, patient with local regional failure. So, and you can begin to see that there may be some clustering of failure patients up here. And then Jimmy asked the question is, can we use early response dynamics to predict what the ultimate outcome will be? So he said, what about week 4, halfway during treatment? What's the median response? And the median response at week 4 was a tumor volume reduction of 32%. So you can see that all the patients who had a 32% reduction by week 4 or more, those were all color-coded in black. They're all local regionally controlled. So on a Kaplan-Meier plot, this looks like this. If you have a robust early response, you have 100% control. Patients that did not respond early, this group up here, all of our failures are in this group. Not everybody in this group is a failure, but all of the failures are in this group, and that's shown in this green Kaplan-Meier curve here. If we now analyze these patients for this PSI value, we can see that this well-responding group has a PSI of 0.75 or less, and our high-risk group in green has a higher PSI of 0.75 or higher. So if we then run mathematical model simulations, for different clinically approved radiation protocols, so all of these patients received once daily radiation, 2 gray once a day. We asked the question, what about hyperfractionation? Smaller doses twice a day, or hypofractionation, which is larger doses less frequently to give normal tissue a chance to recover. So what we are doing here you can see log tumor volume over time for a patient with a high PSI, a medium PSI, and a low PSI. Color-coded are these 3 different protocols. Again, low PSI, I hope you can appreciate a much steeper response than high PSI. We know that already. But what is interesting is that for low PSI, the best treatment is red. Medium PSI, the best treatment is green. High PSI, the best treatment is blue. So the order of which treatment seems to be the best based on the proliferative fraction, which is dependent on this PSI. So this doesn't look like a large difference between blue and green, but remember it's a log scale, so it's about a 50% difference in tumor volume at the end of treatment. So based on this alone, so we know that high-risk patients have a high PSI. We know high PSI are better treated with this blue hyperfractionation. So Jimmy was brave enough to take to a prospective clinical trial. He says, let's take our next 60 head and neck cancer patients that come in. You calculate the PSI. If the PSI is below 0.75, they get standard of care, 2 gray once a day. If the PSI is sufficiently high and we classify a patient as high risk, we're going to treat them with a hyperfractionation. Primary endpoint is tumor volume reduction by week 4. If we now not randomize, but personalize what's the radiation fractionation based on your pre-treatment tumor growth dynamics, can we increase the number of patients that achieve a robust mid-treatment response? The trial results have not yet been published, so all I'm able to show you at this moment is the last line of the abstract we presented at ESTRO. So out of the 59 patients that we were treated, we were able to show that we 12% improvement in the percentage of patients that achieve robust mid-treatment response. So the trial was powered to see a 10% reduction, increase in patients. We saw 12%. So the trial finished early for success. Now that's great. It's a really nice story. We are now taking this forward into personalizing not only radiation fractionation, but also radiation dose, right? Now that we know how to fractionate, up to what dose should we treat? And there's a couple of other tuning knobs we can play with to personalize radiation therapy. But to come back to the didactic side, we used a specific model. I talked about the logistic growth and the logistic radiation response. What Rachel and Jan in the lab have done is actually looked at what if we have different growth laws? How will this model change if we don't have logistic growth, but exponential or Gompertz or what have you? And you can find some of the model selection results in this paper. And then Mohammed has been working with an army of high school students and undergrads to ask the question, what if radiation response is different? What if radiation is not primarily killing cells, but changing the capacity in this logistic model, like killing immune cells or what have you, right? What would this change? And then you get much smoother model simulations. And here's 2 papers about model selection for different radiation response terms. So if you're interested in different mathematical models behind these kind of data, please have a look at those. So for those of you who know baseball, we are now going into the 7th inning stretch and we're going to do some exercises. Does anybody know who that gentleman is? Show of hands. Awesome. Who knows why you know him? What's he known for? So that's George Boggs. And he apparently said this quote, all models are wrong, but some are useful. Now, I would like everyone in the room to please stand up if you ever use this quote. Fantastic. Come on. No, just keep standing. Keep standing. Come on, guys. That's going to be a longer exercise. I need to keep standing up, please. Please, come on, work with me. Work with me. Work with me here. All right, very good. Those of you who know where he said that, please sit down. If you read the paper, please sit down. If you read any of his papers, sit down. All right, so here's public shaming. The folks on Zoom can't see that. But here's an example of us using a quote that we never actually read about and know the context about. So you may be seated. Thank you for being part of it. So for all of you, here's the reference. So that's a textbook on response surfaces, mixtures, and rich analysis. And on page 414, he indeed said all models are wrong, but some are useful in the context of using approximation functions and polynomials to describe different problems. So that's the context in which he said that, if anybody interested. Who's that gentleman? Who knows who that is? Show of hands. Very cool. For those of you who don't know, that's Florian Markowitz, who published a really cool paper called All Models Are Wrong. All models are wrong and yours are useless. Of course, he said this in a specific context of making clinical prediction models. Okay. So, of course, clinical prediction models are not really phenomenological models to test and generate hypotheses. They have a certain purpose. So I'm also in the field of making clinical predictions. So I published a paper together with Olaf Wolkenhauer where we really questioned this notion, are all models really wrong? So as mathematical oncology models are increasingly deployed with the intent to make predictions, a useful model should not be wrong, right? A model that makes wrong predictions is not useful at all. So I think a major hurdle in us trying to talk to clinicians is the language we are using. What's the purpose of the model? What are we trying to achieve with the model? So I think for clinical purpose, predictive models may provide a trigger making. The clinical endpoint for most patients is binary. No clinician has ever asked us, can you predict the tumor volume at the next time point? All they ask us, will the patient progress or not? It's a binary endpoint. There's a certain cutoff. For solid tumors is RECIST. For brain tumors is RANO or iRANO. The question is, will the tumor volume be above or below the threshold? So with that, here's a couple of examples of projects in our group. On the left, Mohammed Zahid, radiation modeling. On the right, Renee Brady-Nichols, prostate cancer modeling. These are like Hurricane or models, as you can see, based on specific time points in a clinical timeline. We make predictions forward in time. So we sample from different distributions and make 100 different predictions. And what you can see in this example here from Mohammed on the left, not a single one of those 100 trajectories actually go through the data points. But 100 out of 100 simulations predict that the tumor volume at the end of treatment will be below this threshold. So although the model does not get the data right, it makes the right prediction, the only task we have for this model. Same for René's work here on the right. You can see 1 out of 100 simulations actually went through these axes. However, sufficiently large number of predictions shown in red here predict that this patient will become resistant to a second round of hormone therapy in prostate cancer. So the model accurately predicted that this patient is of a high risk of progressing. There's another example from Daniel. This is oral cancer, head and neck cancer. On the left-hand side, you can see 5 data points that we have already. These are data we collected. And the clinician, in this case, Christine Chang, thank you, Daniel. Christine Chang would ask, what's the next? Will the patient have progressed by the next time I image this patient or not? So here's 2 models, model 1 and model 2. Make completely different predictions. And here is the data at the next imaging. Which model was better? Who thinks model 1 was better? Who thinks model 2 was better? All right, Perman, you don't count, you've seen this slide before. So model 2 was better. Again, the clinician did not ask us, what's the volume, but will this patient progress or not? Here's the threshold for progression. Well, this should be RECIST, not RANO, I apologize. Model 2 made the right prediction. Although the model is not making the right prediction, the model is not wrong. Okay? The model is fit for purpose. So the model purpose now becomes to accurately predict whether a tumor will shrink below a threshold or not. A large error to data, but the correct outcome classification becomes an acceptable trade-off. So we have stopped trying to train our models to accurately simulate data. The first objective in our fitting objective function is to get the outcome prediction right. And then the secondary objective in these objection functions become fit to data. So while mathematical models may not be right, they do not have to be wrong. So my favorite quote is, do not practice until you get it right, practice until you don't get it wrong. And this quote is, of course, not from me, but from a Tom Clancy book. That's Mark Cameron who wrote this. So if you like spy novels, here you go. And there he said it. Don't practice until you get it right, practice until you don't get it wrong. So coming back to the didactic part. Before ChatGPT, we used to look on Wikipedia. So here's what Wikipedia says. What's important here is what's the purpose, and sometimes the purpose is forecasting and predicting. So when we are building models to make predictions, we have to follow certain steps, and that's a pipeline that Renee and I have put out. That photo is from last night, so it's the most up-to-date talk we can get. That's why I didn't have it finished until a minute before the presentation. Anyway, we wrote a paper called Mathematical Models of Cancer, When to Predict Novel Therapies and When Not to. So here's our proposed standard. We identify a putative biomarker. These are variables you can measure in clinical data samples. Develop a mechanistic model, calibrate the model with existing data, validate it with data it hasn't been trained upon, then evaluate the predictive performance for known the biggest market for predictive modeling is baseball statistics, right? So nobody will buy a new baseball statistics model if you cannot prove that you could predict the right players to buy in the last transfer period. I give you all the data I had last year and the year before. Show me that the model would have picked the winner. Then and only then we're going to buy your software to help us predict next year's player to buy. So we have to show what's the prediction accuracy on an outcome that we know. And only if this is high enough, and we have still to talk with different clinicians about for what problems, what's the bar we have to clear. But once the accuracy is high enough, we can then go forward and simulate and predict unknown treatment. What's very important is not to take any shortcuts, okay? So in the last couple of minutes, I want to talk a bit more about the calibration box that is here. And here you go. This is my favorite quote is I found parameters in the literature. So couple of words of caution. Mice are not men. In vitro is not in vivo. Breast is not prostate. Molecular scale is not organ scale. Seconds are not days. Your model is not my model. Don't pick and choose parameters out of context and plug them into your model, and now the model fits data and say the model is calibrated. I see that we've done this exercise a couple of times, but just taking parameters out of a model that was developed for a different purpose may not translate and may potentially lead you down a wrong path. Who's that gentleman? Anybody seen him before? Anybody seen him before? William of Ockham. So here's my favorite George Box paper. He actually wrote about William of Ockham. And here's another quote of his. The ability to devise simple but evocative models is the signature of a great scientist. Over-elaboration and over-parameterization is often the mark of mediocrity. And he quotes William of Ockham, which is, of course, Occam's razor, which is known as the principle of parsimony, to try to develop the most parsimonious model that describes your data the best. So I would like to invite all of you, if you want to include a George Box quote in your next presentation, let's use this one. The ability to devise simple but evocative models is the signature of a great scientist. So I was at a workshop that Renee and Sarah and Kathleen have organized at the Fields Institute. And Harsh Jain gave a talk, and he introduced the concept of Heiko's razor. I don't know why, but here's my favorite quote. If you have two parameters, you may have one too many. And with that, I'm happy that nobody has thrown tomatoes at me yet, so I'm going to stop here. I want to thank the people in my lab. That's my new group at MD Anderson. Nahum, Goja, Shambhavi, and Perman are here. So there's going to be at least one more poster tonight. If you're interested, please stop by. Big thank you to the collaborators at MD Anderson and Moffitt Cancer Center that I had the pleasure of working with over the past many years. And while I'm taking questions, I put up a couple of references of some of our very opinionated opinion papers where we lay out how to integrate mathematical models into the clinic. With that, thank you for listening. I don't have a mic here now.
Thanks, Heiko. If I understand your model right for your saturation index, you're taking 2 time points, using those 2 time points to fit a PSI for the individual. So for individuals that may have more than 2 time points available, have you ever checked to see that whether or not you take point 1 and 2 or 1 and 3 or 2 and 3, you get the same PSI? Because it seems a little bit like that slope is essentially mapping on to a master curve that you believe to be appropriate.
Yes.
And how did it work?
So a couple of different things. So we only pretty much get 2 untreated data points. Every subsequent data point is treated. So ideally, we want to make decision about treatment prior to delivering treatment. What we have done is we are looking at the response then. Oh, I took these slides out. So that's a concept we're calling DART, Dynamics Adapted Radiation Dose. We take the pre-treatment growth dynamics and the on-treatment response dynamics to make adaptive Bayesian predictions forward in time into what's the maximum dose we should to control the tumor. What we haven't been able to do is look at different untreated time points to see if other combination of data points will give you the same parameter, just because these data don't exist.
How different are the starting sizes?
Say that again, please.
How different are the starting sizes of these tumors?
I can.
Are they millimeters to 10 centimeters? I mean, what are we talking about here? Are they all roughly the same size, or are there radical differences?
There's quite a spread, actually. Some are also nodules, some are primaries, and the primaries actually vary quite a bit. What is interesting is taking pre-treatment size does not correlate with response.
I would agree with that.
It does not correlate with response. You can have, in fact, in these head and neck cancer studies, we have seen fairly large tumors that are not growing before treatment. And that's important. So it's the first time we looked at that, right? Time point 0 for the radiation oncologist is, oh, the patient is referred to radon. We take an image, we plan treatment, and that's our baseline. But that's not baseline for the patient, right? Just starting at going back to the diagnostic images, actually we see so many tumors that are very slowly advancing. And if we are now classifying stable disease, right? We irradiated this tumor for 5 weeks and we now have stable disease. That tumor wasn't going anywhere before treatment. So treatment may not be a response metric, right? It's very interesting to actually decipher some of these dynamics. So size does not seem to be really correlating with response and outcome. It's fascinating. Good questions, though. Thank you. Mary. Oh, sorry, shoot.
Make it quick. So, beautiful data, Heiko. It's a quick question. So just clarification. I don't see any non-responders in your cohort. Like almost everyone responding. Is it like you guys don't want to include them, or is it just because you keep that 6 weeks maximum? Just trying to understand the model.
Yeah, so in this cohort of these 59 head and neck cancer patients, we had about 13 non-responders. So head and neck radiation is incredibly successful, especially in HPV-associated cancers. They are fairly radiation sensitive. So the biggest next step for this work is to schedule de-escalation. Given that we are so good in curing some of those patients, how much can we de-escalate without sacrificing cure? If we are now looking at non-HPV associated head and necks, smoking and alcohol related, they are much more resistant. They're just not as prevalent, so we don't have a large enough data set to calibrate these models. So for now, it's only this.